Concrete pool shells provide a highly conductive view for ground. Concrete pools have extensive rebar embedded in the concrete, which is in direct contact with the soil. Additionally, the deep end of the pool is often at the same level as the groundwater table. Consequently, the concrete pool shell acts as a low-resistance ground electrode. Typical power supply to pool equipment includes a number 10 stranded THWN ground. Most power runs to pool equipment use number 10 stranded THWN wire as the ground conductor. This wire runs from the main panel at the electrical meter to a subpanel located at the pool equipment. Average residential ground connections at the meter are often inadequate. In many homes, the ground connection at the electrical meter consists of two 8-foot ground rods driven into dry, sandy soil. However, these ground rods may not be deep enough to reach the groundwater table, resulting in high resistance to earth. Due to the excellent grounding provided by the concrete pool shell and the number 10 ground conductors in the power runs, any electrical surges or lightning strikes that reach the electrical meter will readily flow through the ground path provided by the pool. This ground path is more likely to be effective than the average residential ground connection at the meter, which is often compromised by high resistance to earth. Consequently, the excessive surge current will primarily flow through the number 10 ground conductor to the pool panel. This scenario presents a potential hazard. Firstly, the number 10 ground wire may be undersized to handle the surge current from a lightning strike. Secondly, the surge current flowing through the grounding system can damage sensitive pool equipment. Thirdly, it creates a potential safety hazard for anyone in or around the pool during a surge event. To mitigate these risks, consider the following measures. 1. Ensure the main electrical service has adequate surge protection installed. This will help to divert some of the surge current away from the pool equipment. 2. Upgrade the grounding system at the main electrical service. This may involve installing additional ground rods or using a ground plate to improve the connection to earth. 3. Consider using a larger ground wire for the power runs to the pool equipment. While number 10 may be acceptable under normal circumstances, a larger wire can provide a lower impedance path for surge currents. 4. Install surge protection devices at the pool equipment subpanel. This will help protect the equipment from any residual surge current that makes it through the main surge protection. 5. Ensure all bonding connections around the pool are properly installed and in good condition. This includes bonding the pool equipment, metal parts of the pool structure, and any nearby metallic object. 6. Consult with a qualified electrician to assess the specific grounding and bonding requirements for the pool installation and to ensure compliance with all applicable codes and regulations. 7. Regularly inspect the grounding and bonding system to ensure that it is in good condition. Look for signs of corrosion or damage and repair any problems promptly. 8. Consider the soil conditions in the area. If the soil is particularly dry or sandy, it may be necessary to take additional measures to improve the grounding system. This could include using ground-enhancing compounds or installing a chemical ground rod. 9. Understand the limitations of grounding and bonding. While these measures can help to reduce the risk of electrical shock and equipment damage, they cannot eliminate the risk entirely. 10. Educate yourself and others about electrical safety around pools. This includes avoiding the use of electrical appliances near the pool, keeping electrical cords away from the water, and knowing what to do in the event of an electrical emergency. Furthermore, it's important to understand the role of the equipment grounding conductor, or EG. The EG, typically a green or bare copper wire, provides a low impedance path for fault current to return to the source. This path facilitates the operation of overcurrent protective devices, such as circuit breakers or fuses, to quickly clear a fault and minimize the risk of electrical shock. The size of the EGC is determined by the size of the ungrounded conductors in the circuit, as specified in the National Electrical Code, or NEC, Table 250.122. For example, if the circuit conductors are number 10 AWG copper, the EGC must be at least number 10 AWG copper as well. When dealing with pool installations, it is crucial to pay close attention to the bonding requirements outlined in NEC Article 680. Bonding refers to the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed. The purpose of bonding is to minimize voltage gradients in the pool area, which can cause electrical shock hazards. All metal parts within 5 feet of the inside walls of the pool, and any metal parts that are in direct contact with the pool water, must be bonded together. This includes metal conduit, metal fences, metal door frames, and any other metal objects that could become energized. The bonding conductor must be solid copper and must be at least number 8 AWG in size. It is important to note that the bonding conductor must be continuous and unbroken. Splices are not permitted in bonding conductors. The bonding conductor must be connected to a common bonding grid, which is typically a network of interconnected copper conductors buried in the ground around the pool. The common bonding grid serves to equalize the electrical potential in the pool area and to provide a low impedance path for fault current to return to the source. In addition to the bonding requirements, the NEC also specifies grounding requirements for pool equipment. All pool equipment, such as pumps, filters, and heaters, must be grounded to the equipment grounding conductor. The size of the equipment grounding conductor is determined by the size of the circuit conductors, as specified in NEC Table 250.122. It is important to note that the equipment grounding conductor must be connected to the equipment grounding terminal in the equipment enclosure. The equipment grounding terminal is typically a green screw or a green wire connector. When installing electrical equipment near a pool, it is important to maintain the required clearances from the pool water. The NEC specifies minimum clearances for luminaires, receptacles, and other electrical equipment. These clearances are designed to minimize the risk of electrical shock hazards. For example, luminaires installed within 12 feet horizontally of the pool water must be at least 12 feet above the maximum water level. Receptacles installed within 20 feet of the pool water must be ground fault circuit interrupter, or GFCI, protected. In addition to the NEC requirements, it is also important to follow the manufacturer's instructions for installation and maintenance of pool equipment. The manufacturer's instructions may provide additional safety precautions and installation guidelines. When working with electricity, it is important to take the following safety precautions. Always turn off the power at the circuit breaker before working on any electrical equipment. Use properly insulated tools and equipment. Wear appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work on electrical equipment when you are wet or standing in water. If you are not comfortable working with electricity, hire a qualified electrician. The UFA-ground, also known as a concrete encased electrode, is an effective grounding method due to the large surface area of the concrete in contact with the earth. This provides a low impedance path for fault current to return to the source. The NEC requires that a concrete encased electrode be installed in new buildings and structures that have a concrete foundation or footing that is in direct contact with the earth. The concrete encased electrode must be at least 20 feet in length and must be encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. The concrete encased electrode must be connected to the building's grounding system with a number 4 AWG or larger copper conductor. The ground rods are often used in residential grounding systems. Ground rods are typically 8 feet long and are driven into the earth. The NEC requires that at least 2 ground rods be installed at least 6 feet apart. The ground rods must be connected to the building's grounding system with a number 6 AWG or larger copper conductor. The effectiveness of ground rods depends on the soil conditions. In dry, sandy soil, ground rods may not provide a very effective ground. In wet clay soil, ground rods will provide a more effective ground. Ground plates are another type of grounding electrode. Ground plates are typically made of copper or galvanized steel and are buried in the earth. Ground plates provide a larger surface area than ground rods and are therefore more effective in dry, sandy soil. The size of the ground plate is determined by the size of the building's electrical service. The ground plate must be connected to the building's grounding system with a copper conductor of appropriate size. Chemical ground rods are ground rods that are filled with a chemical compound that helps to improve the conductivity of the soil. Chemical ground rods are often used in areas with poor soil conditions. A chemical compound in a ground rod helps to attract moisture to the soil, which improves the conductivity of the soil. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the surge current away from the electrical equipment and back to the grounding system. SPD are typically installed at the main electrical panel and at subpanels. There are three types of SPD: Type 1, Type 2, and Type 3. Type 1 SPD are installed at the service entrance. Type 2 SPD are installed at subpanels. Type 3 SPD are installed at individual pieces of equipment. Ground fault circuit interrupters, or GFCIs, are used to protect people from electrical shock hazards. GFCIs work by monitoring the current flowing through circuit. If the current flowing through the circuit differs from the current returning to the source by more than 5 mA, the GFCI will trip and interrupt the circuit. GFCIs are typically installed in areas where there is a risk of contact with water, such as bathrooms, kitchens, and outdoor areas. Bonding is the process of connecting all metal parts of an electrical system together to create an electrically conductive path. Bonding helps to minimize voltage gradients in the event of a fault and reduces the risk of electrical shock. Bonding is required for all metal parts of an electrical system, including metal conduit, metal enclosures, and metal equipment. The bonding conductor must be sized according to the size of the circuit conductors. Electrical codes such as the NEC provide detailed requirements for grounding, bonding, and surge protection. It is important to follow the electrical codes to ensure the safety of electrical systems. The NEC is updated every 3 years. It is important to stay up to date on the latest changes to the NEC. Licensed electricians are trained and qualified to install and maintain electrical systems. It is important to hire a licensed electrician to perform any electrical work. Unlicensed electrical work can be dangerous and can void your insurance policy. Regular inspections of electrical systems can help to identify potential problems before they become hazards. It is important to have your electrical system inspected regularly by a qualified electrician. Lightning is a powerful force of nature that can cause significant damage to electrical systems. Lightning strikes can generate voltage surges of hundreds of thousands of volts. These voltage surges can damage or destroy electrical equipment. Lightning protection systems can help to protect buildings and structures from lightning strikes. Lightning protection systems typically consist of lightning rods, grounding conductors, and surge protection devices. Static electricity is a buildup of electrical charge on a surface. Static electricity can be generated by friction, such as rubbing two objects together. Static electricity can cause sparks and can damage sensitive electronic equipment. To reduce the risk of static electricity, use anti-static mats and sprays. Humidity can affect the conductivity of the air. High humidity increases the conductivity of the air, which can increase the risk of electrical shock. Dry air decreases the conductivity of the air, which can increase the risk of static electricity. Temperature can affect the resistance of electrical conductors. Higher temperatures increase the resistance of electrical conductors. Low temperatures decrease the resistance of electrical conductors. Corrosion can damage electrical connections and reduce their conductivity. Corrosion can be caused by moisture, salt, or other chemicals. To prevent corrosion, use corrosion-resistant materials and apply protective coatings. Vibration can loosen electrical connections and cause them to fail. To prevent vibration-related failures, use vibration-resistant connectors and supports. Electromagnetic interference, or EMI, can interfere with the operation of electrical equipment. EMI can be caused by radio waves, microwaves, or other electromagnetic fields. To reduce the risk of EMI, use shielded cables and enclosures. Power quality refers to the stability and reliability of the electrical power supply. Poor power quality can cause electrical equipment to malfunction or fail. Power quality problems can be caused by voltage sags, voltage swells, harmonics, or other electrical disturbances. To improve power quality, use power conditioners and uninterruptible power supplies. Electrical safety is a critical concern, especially in environments like pools where water and electricity can create hazardous conditions. Understanding the principles of grounding, bonding, and surge protection is essential for ensuring the safety of people and equipment. A properly designed and installed electrical system can minimize the risk of electrical shock, fire, and equipment damage. Regular inspections and maintenance can help to identify and correct potential problems before they become hazards. In addition to the technical aspects of electrical safety, it is also important to educate people about the risks of electricity and how to avoid them. This includes teaching children about the dangers of playing near electrical equipment and reminding adults to be careful when working with electricity. By taking these precautions, we can help to create a safer environment for everyone. The information provided is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician to ensure that your electrical system is safe and complies with all applicable codes and regulations.